Hi. Does this work? Oh, awesome. Cool. Are you excited? I am excited. Let's get started. So I've been working on this thing called signature inference for the last 6 months, and this was my master thesis. And I'm now going to present to you what I think could be revolutionary in the industry. In practice, of course, it's not that exciting. All right. So I am going to be giving a talk for about 30 minutes, which means I had to cut out most of my script, and I'm going to jump across most of the motivation and start with this. If you think writing correct software is easy, then I have to do the entire motivation anyway, but if we can just all get on the same page about this one sentence, that writing correct software is hard, then I can skip all of that and just start here. So I start from the assumption that writing correct software is hard, and one of the ways we try to do it anyway is by writing tests. I'm also skipping over all of the other things you can do to write correct software. So the kind of tests we usually write are called unit tests, and they look a bit like this. So this is a Boolean expression, but with the right wrapper code, this could be a test suite. And here you see that if you sort this specific list, then you get this specific output list. So you're describing what happens when you give some input to a function, you describe the exact output, and you then assert that this is in fact the case. Now, there are two problems with this. First of all, you're going to need as many examples as there are code paths in your code, at least, to have any chance at getting your code correct. In fact, this is often phrased as you cannot check whether your code is correct, you can only check if it's not correct. And this is the first problem with unit testing. The second problem is that you now have to write all of these examples. You have to come up with them, you have to write them down, you have to make sure that you run all of them, and this is called the cost problem. The first problem is called the coverage problem, the second problem is called the cost problem. So in Haskell, we have had for a while a solution to the coverage problem, and this is a probabilistic solution where instead of just running a piece of code, checking if the assertions are correct and it doesn't crash, now we give an argument to that piece of code, and we check that if you throw any input at that piece of code, then the assertions hold and that it doesn't crash, etc. So in this case, this is what we call property testing. You say for any arbitrary list, if you sort the list, then it becomes sorted, is the test you see here. So we literally say for all arbitrary lists, if you sort the list, then it becomes sorted. Now this probabilistically solves the coverage problem in that as long as you throw enough input at it, you will most likely cover all your code paths, and then you can be sure that, given that you have the right properties, your code actually works. But this exacerbates the cost problem in that now you don't just have to think of input-output examples, which we usually consider quite easy, but is nonetheless annoying. Now you have to write generalized properties, which to most people, including myself, is actually even more annoying than writing individual test cases. Now, the concept of property discovery is where we are going to try to eliminate coming up with these properties yourself so that we can solve both the cost problem and the coverage problem of testing and make it easier to write correct code than it would be to write incorrect code without any tests. So if we can somehow make sure that you don't have to come up with these properties manually anymore, then we can solve the cost problem, and the coverage problem has been solved by the fact that they're property tests. All right. So there exists something that does this. It's called QuickSpec, and this has been around for a while. That's not true. It's been around since 2016. There are a few papers about it. It's not very well known, and I will get into why that is the case in a moment. But this is a Haskell library, and I'm going to show you a bit of how it works. I didn't write this. I'll get to that in a moment. So here's an example. Here you have some example code. You don't have to actually read it. These are the important parts. You have a sorting function and a function that checks whether a list is sorted. And now we're going to try to run QuickSpec on it. QuickSpec finds that these functions are relevant in the code. So you have, I'm going to skip over the fact that constants are not functions and just assume that they are. You have these functions here. QuickSpec finds them and then gives you some output. And it tells you all of these things are probably true. Now this is, first of all, there may be false positives. In this case there aren't, but there could be. Second, not all of them are relevant. These are the ones that we're interested in. So these are properties that it discovers, like if you sort a list, then it's sorted, or if you sort a list twice, it's the same as sorting it once, etc. The problem is, to run QuickSpec, you have to write a bunch of code. And in fact, this is about double the amount of code than the code you were trying to analyze. And if you're using QuickSpec to get yourself out of writing tests manually, then you're never going to write this much code in order to be able to run it. So that's one of the problems with QuickSpec. You have to write this bunch of code. Another problem is it only works for monomorphic functions because you can only generate input if you know which type the input is going to be. So you have to explain to QuickSpec manually that filter is a function that works from capital A to bool, yada yada. And this QuickSpec then knows that if you use a capital A, it's actually a parameter, so it's built in. And so it will figure out that you can actually substitute A for anything. But you still have to manually monomorphize all the functions in the code that you're interested in. You also have to describe all of the functions that you're interested in. So your entire parts of the code that you're looking at must be described. You have to write a bunch of code. And then the last problem is that this is really, really slow. If P is the size of the properties you're trying to discover, and N is the size of your code base, then this is of order N to the power 2P. So this is ridiculous. And you wouldn't be able to run this on your entire code base. And the reason is, QuickSpec is actually very smart, but the stupid version of what it actually does is it generates all possible terms, all possible equations, makes sure that they type check, make sure that you can generate the input and check the output for equality, and then run quick check on those properties. And whatever is left over at the end, you print that. QuickSpec is actually a bunch smaller. There are papers about how they optimize this, but it's still rather slow, and this dumb version can give you an idea of why. So we set out to make something better. And now I'm going to be talking about the work I did. We made something called EasySpec, and it's supposed to solve the problems with QuickSpec such that property discovery becomes something feasible so that you can actually run it on your own code without the problems of having to write code manually and the speed problem. So the first step to getting there was to automate the part of writing all of that code manually, right? So you saw that you have to write a bunch of code. Here it is. You don't really want to do that. But as some of you may have guessed, this is automatable, right? So this is the part that you actually have to be able to generate. The rest is sort of wrapper code. And this is the relevant part of the code that you have to generate. So the input to QuickSpec is called a signature. A signature contains the functions that you're interested in. They have to all be described, otherwise QuickSpec has no idea what they are. And you can, as part of the optimization that QuickSpec does, also give it some properties that it should already know about and not rediscover. And then there is this one function called QuickSpec, which turns a signature into a signature after doing a bunch of discovery. And then in the signature as the output, you get the properties that were discovered in the properties field of the signature back. This is what we were working with, right? So now we're going to try to figure out which functions are in scope in the module automatically. We use the GHC API to do that, and then generate one of these signatures in code, run GHCI on it, and then get the output automatically. That was the idea of the automation part, right? So the hardest part here is to generate the expressions that represent the functions that we have in our module. So if we find one of these functions like filter here, for example, first we have to make it monomorphic. It's a little harder under the hood, but it essentially boils down to uppercasing the type variables. And then we give it a name, which we can also get from the API, and we have to annotate the type manually, and we can get the type from the GHC API as well. And then we put all of them together in a list, and then we essentially get the signature expression that we were looking for. We run GHCI on it, and we can get our properties. So here is an example. This is the situation that we were at that point after the automation was done. We have a module here that has exactly 2 functions in scope and very purposefully only reverse and sort. Then we run EasySpec on it, and we find the properties that we would expect. In this case, list. If you reverse a list twice, you get the original list, and if you sort a reverse list, it's the same as sorting an unreversed list. Now, we have automated the part of QuickSpec, but it's still very slow. Let me walk you through it. You have a plot here. It's a log plot. So on the y-axis, you see the runtime of how long it took to run EasySpec. On the x-axis, you see the number of functions that were in scope in the module that we ran it on. This is a log plot. So you can see for 15 functions, it already takes 5 minutes to run, which means you're not going to run this on your bank. You're not going to be able to run this on real code. It's just too slow. So it still has the speed problem of QuickSpec, but now it's automated in the sense that you don't have to write all this code manually anymore. So the second part is about how we will try to make it fast enough so that you can actually run it on your own code. But first I have to make a little detour and define what properties are. A property is essentially something with an equals in the middle that type checks. So an example is reversing a list twice is the same as the original list. This is short for the equality of two functions that each have an input called ls or whatever you want to call it. Each have an argument, and both of the arguments need to be generatable by randomness. In this case, lists, they can be. And the output needs to be checkable for equality, so we can actually check if the equation holds. All right. Now, the reasons that QuickSpec and therefore EasySpec by extension are slow is the first factor is how big the properties are that we are trying to discover. And in fact, the default is 7. So we try to discover properties of maximum size 7. But because we fix this, this is actually not going to be relevant in the complexity analysis. It's just necessary to mention this. And the second problem is how many functions are there in your code base? And how many functions there are in your code base is not necessarily relevant, but the part that's relevant is how many of those do you give to QuickSpec? And this is called the size of the signature. Now, the big idea was that we're not usually interested in all of the code base, but we're interested in the last part we wrote, or a very small part of your code, actually. So maybe we can find a way to give a smaller signature to QuickSpec than our entire code base, and still find all of the properties of the function that we're interested in, but not all of the properties of all of your other code. So the first idea was to just reduce the size of the signature by making this function called inferSignature that you can describe by saying that the inputs are the functions that are in scope and the functions that are in focus, namely the ones that you're interested in. And then it will output a chosen number of functions from the scope functions that is hopefully smaller than your entire scope, and then give that to QuickSpec. And then a function that does this is what's called a signature inference strategy. And the two degenerate ones are called full background, which just says everything is relevant. The entire scope will be given to QuickSpec. And the other one is empty background, which says only the ones we're interested in are relevant. Now, you could say, well, that's obviously the best one. The problem is, if QuickSpec doesn't know about a function, then it cannot discover anything about it. So if you only give QuickSpec the one function you're interested in, you're only going to find properties like if you run it twice, it's the same as running it once, or if you run it twice, it's its own inverse or something. Any property that only relates that single function to itself can be found with this empty background strategy. And these degenerate strategies actually allow me to show you some plots and explain the plots before we delve into the other strategies that we looked at. Here we have the runtime of full background and empty background in terms of the size of the scope of the functions. So on the y-axis, you see the runtime. On the x-axis, you see the number of functions in the signature. Label is wrong. This should be signature. So the number of functions in the signature. And this is not a log plot. This is a linear plot. Did you have a question? And then we put together a whole bunch of code examples and ran EasySpec on all of the different functions that could be in scope, all of the different functions that could be in focus on all of the different examples. And then we looked at how many equations were found in the end that were relevant to the function that we were interested in. So in the case of reverse, it would not be relevant that if you sort something twice, it's still sorted. But any property involving reverse would be relevant. So if we run EasySpec on all of our different examples, we find that full background finds this many, like yay many, relevant equations, but empty background finds a lot fewer of them, because of course it only finds the properties that only relate the focus function to itself. Does this box plot make sense? Because I'm going to show you a bunch more of them. All right. So here is the first non-trivial strategy we looked at. If we assume that there is only one function in focus, and this can be extended, of course, then what we do, this was the silliest thing we could think of. You take the 5 closest functions by name. So the 5 functions that are most similar to the function you're interested in by name. All right? So if you're interested in a function called isPrime that checks if a number is prime, then this would select functions like a prime constructor or prime deconstruction, factorization, etc. Those functions. And it makes sense that some of them would be relevant, but it's rather obvious that this is actually not as good as you would want it to be. Nevertheless, the runtime is a lot better because, of course, if you only take 5, then this is constant time. If you take I, then this is linear time in I, of course, but we take a fixed amount on purpose. And then this is actually annoyingly good when it comes to relevant equations. So we find a surprisingly large number of relevant equations. Now, we tried this with a few other strategies, like looking for distances in something else than the namespace. This is the syntactic similarity of symbols, which means we look at the difference in the implementation of the functions. So we look at which other functions occur in the implementations of the functions that we're interested in, then group them together and take the 5 closest ones to the focus function. And this is this would be useful, we thought, because if you look at the prime example again, most of the functions dealing with primes will all have either modulo or quotient or divide functions as the implementation, so they would be relevant to each other. We find, of course, this is constant time again. This is not better, not much worse either. Still annoyingly good because this was so simple, really. And then we also looked at the type, where we look at the distance between the types of the functions, so how similar the functions look by type. And then the idea here is that if all of your functions deal with, if your focus function deals with a list, then other functions that deal with lists are probably going to be relevant. So that was the motivation here. Similar, it's also constant time. It's not better, not worse. So we really couldn't think of much else to try than just these 3 different aspects of your code until we found this one breakthrough. Of course, we didn't find the graph. I found the thing, and then I made the graph so I can show you. This is a histogram of the number of different functions in any equation. And what you see here that most equations contain very few different functions. In fact, 60 to 70% of all the equations only contain 1 or 2 different functions, and up to 90% only contain 3 or fewer different functions, which means that giving a signature to QuickSpec that is very large, like for example 20 functions, isn't going to be useful given that it has this terrible complexity. Oh, sorry. So the idea now was to maybe run QuickSpec more than once and then give it very small signatures and combine the equations at the end. So then we thought of this new definition of the signature inference strategy, where you have a list of signatures to give to QuickSpec and then run QuickSpec on all of them, find all the equations that relate the functions that you're interested in, and then combine all the equations in the end. If you remember at the start, I said that you can give previously discovered properties back to QuickSpec to use in its optimization. And if you want to do that, our idea was to maybe we can put them in a tree or in a forest, these signatures, so that you can run dependent signatures before the previous ones so that they can use each other's results in the optimization. If you can do that, may as well share the previous runs and make it a direct acyclic graph. And now we came up with the first thing that would be using this new power of this kind of strategy, but was still rather simple. And we were looking to get at the 60 to 70% of the equations that only had one or two functions in it. So the idea was to make tuples of all the functions where one is the focus function and another is any function in the scope. And if you make this linear number of tuples and you put them each in the signature, and you also make a separate signature that only contains the focus function, you make this kind of graph. Then the idea was to run QuickSpec on all of these tuples separately, gather all of these equations that you would find that only relate these two functions, and then combine them all in the end. This would take linear time instead of n to the power 14, and we'd get about 60 to 70% of the equations. That was the idea. Now, it runs a lot quicker as expected, and then we found this. It finds more. So we've actually already beaten QuickSpec by just running it a bunch of times with very small signatures. And I'm not going to go into how it's possible that it can actually find more, because that's a rather technical bit, but I can do that afterwards if you'd like. But now we thought, well, if we can do this with just tuples, who knows what else we can do, right? So let's try something else. We also tried to look into, maybe we want to not run QuickSpec after we found something beforehand. So we'd want to be able to look into what the previous runs had found before we run something else, so that we can have conditional nodes in this graph. And then we came up with this weird directed acyclic graph of functions. It was nasty to implement and not really fun to write. Threw it away very quickly. And then we came up with this syntax tree idea, which is where an inferred signature is actually a syntax tree of a computation that you could run to decide when to run QuickSpec or not. So if you don't know what generalized algebraic data types are, feel free to ignore most of this. The idea is here that you just describe the intention to run QuickSpec, and then the interpreter for this syntax tree would take care of the rest. And here you say, here is a signature that we give to QuickSpec to run. We get the equations that we find, and we also get this thing called an opti token, which is used to signify that if I give this opti token to a run of QuickSpec, that means use the properties of that specific run in this subsequent run that we're going to do right now. Again, we tried to make something really simple that would take care of this new expressive power, which we called chunks plus, which is exactly like chunks in that it runs all the tuples first, but then it also conditionally runs triples, runs QuickSpec on triples. So the idea of the condition is that if sort and reverse are put together in a signature, and they find functions that are related to the focus function sort, and another node, sort and not, both, if they both of these nodes find properties that are relevant to sort, then it's likely that if you put them all three together, you find even more relevant stuff. That's the idea. So then we conditionally run QuickSpec on this third node of triples. All right. As you would expect, or you would expect this to have quadratic complexity in the worst case, because you can have a quadratic number of signatures to run QuickSpec on. Still faster though. And now we find that we can actually find a lot more than just running QuickSpec by itself. So we found we can find more than we thought we did, but this is still quadratic time. It's still going to be too slow if you have a big code base. But it turns out this is a really good building block for what comes next. But let me step aside for a moment. Here's the current state. We can run EasySpec on code in a reasonable number of time and get the relevant properties of the function that we're interested in, namely sort. I will give a small demo at the end as well. So this is the current state of where we're at. We still wanted it to be possible on realistic sizes of code bases, because this is of course only a module with two functions. We wanted it to be possible for large code bases and make it actually practical, so I could use this in my own code, right? Oh, there are a few slides missing. Anyhow, I can go over them afterwards if it's relevant. Spoiler, we managed to do it in constant time by combining composing these strategies, but it looks like my slides are missing, so I'm going to have to skip that. Now, this looks really cool, but I wrote this for my thesis, so it doesn't actually work. I had to write a thesis. And when I say it doesn't actually work, it's that there are some technical problems that could be solved, but we just haven't had the time to do it. So one of the problems is that it only works if your module only contains functions that are exposed for which the types are also exposed. And this already doesn't hold for the prelude, so any of your modules that import the prelude, this is not going to work on. This is fixable, we just haven't done it. It doesn't work for partial functions. It only works with built-in instances. So if, for example, your functions work for orderable lists or lists of orderable things, then the orderableness has to be defined within QuickSpec because we don't have a way to collect the instances yet. Can be fixed as well. The arbitrary instance has to be in scope in the module that you're running this on, which is usually not the case because your arbitrary instance is in your test suite and not in your library. This doesn't work well with the C preprocessor because of how we do the translations to the GHC API. It also doesn't work very well if you have higher kind of type variables in, for example, length, which has an arbitrary foldable, I think. Because there is no way to monomorphize higher kind of type variables per se. So we haven't done that either yet. These are all technical problems. These are not theoretical. These are all technical problems. They're not theoretical problems. We could fix them, but we haven't put enough time into this problem. And then there are also some research problems, like can we do it faster? We have something either constant, linear, or quadratic time, but it's still seconds and not milliseconds. We've only chosen functions from the modules that we're interested in, and we've not actually tried to construct new functions to give to QuickSpec. For example, if your code deals with numbers, you probably want to give 0 as a constant. If your code deals with lists, you probably want to give the empty list as a constant. Even though it's generated separately, sometimes there are laws that only hold for specific constants. We haven't tried to apply this to any code that involves I/O. We have tried to evaluate the different strategies by how many relevant equations they find, but we haven't tried to figure out whether some relevant equations are better than other relevant equations. We've actually recently considered that we may want to do mutation analysis on this by looking at if you change the code, does the property still hold? Yes, then it's probably not a good property. So that kind of thing we could do, haven't done it yet, could be further research. And now, the reason I'm here is because I would really like this to work. And here are some links. If you're interested in this, come and talk to me afterwards because we need manpower to actually make it work. And we need to make it production ready because this is just a proof of concept. So if you're interested in doing this, come and talk to me. All right. So a little more about me. This was my master thesis. I wrote Haskell in open source. I used to teach Haskell at the university, and now I write Haskell in industry. Here are some more links if you want. You will also be able to find the link to the slides of this talk on there somewhere afterwards.
All right, thank you. Thanks very much. Any questions? One question in the back.
Hey, thank you for the talk.
Thank you.
And I would like to ask you about, as a perspective of a developer, and I'm writing my code, and you mentioned that actually we can change, or we can check the code we recently changed. So there is some kind of mechanism where we can pick up functions. Is that true? Or did you try this approach? This is my first question.
Did I try? Sorry, I didn't get what the approach was that you're describing.
So if I'm changing my code and I get a git diff, and from that git diff, I can see what has changed, and I can just ask this solution for the relevant properties that I already changed in my code. Have you talked about this?
I'm still not sure. The reason I'm unsure is because you're supposed to run this EasySpec in the background while you're writing code. So I write my function, I run EasySpec to see if there are properties. If I change my function, I will write EasySpec again, or I will look at the test suite again and see if it still holds. So I'm not sure what you mean by the git diff there.
Mm-hmm. So you can check. You can just only check the whole program solution. You cannot say, please search properties only for this function for me.
Well, that's exactly what this is for. So in the case of QuickSpec, you can only look for all of the properties of all of your code, but EasySpec is specifically for, I want the properties of this function. That's actually also the only reason it works. Because if you didn't do that, then you had this complexity problem again.
Okay, so that's good. And could you implement a strategy where actually you combine your function under test with different function from the functions that actually call this function? So like picking up the expression, where, for example, when I have a function f, and I'm picking up different functions from my function space, which actually contains this f function, for example, g1, g2, gn, and I'm combining these combining gn's with my f function.
Mm-hmm.
Have you implemented such kind of strategy?
So there are two relevant ones here. So one of the ones I described was where you look at the implementation, which means the functions that my function calls. What you're describing is the reverse thing, I guess. We haven't tried this, mainly because in order to do this, you need functions that are being called. And we wrote all the code manually, so it usually wasn't very intertwined with each other. The reason we wrote all the code manually is because of the practical problems I outlined. None of the libraries on HaskellX could actually be used for my evaluation. So I had to write a bunch of examples manually.
Okay, thank
you.
you.
This is a good idea. We thought about this. I'm going to answer one question that I usually get without anyone asking it. This only works for code that already works, in the sense that you will only find properties of the code that your code already has. So you can't find properties that you want to have hold that don't actually hold yet, which is, I mean, not fixable, but also exactly what you'd expect. Yes.
Thanks.
Should work.
In a similar way, I guess it would also help that you have written some interesting functions which are relevant to your problem space, like is sorted and things like that. If you haven't actually written is sorted, then it can't generate that for you. So
yeah, that's right.
So it seems like it's pretty useful if you've already done a lot of work rather than helping you very incrementally. Is that right?
Yes. Although usually you find that the functions you're writing are composed of the functions that you've already written and are therefore relevant. Also, usually a lot of functions that are relevant that you would never think were relevant. Also, you find some silly properties like the function all that checks if a list, every element of a list satisfies a predicate. We found a property that says if you drop all the elements of your list, then for any predicate, all works. So you find some silly stuff, which means you still have to go through the properties manually and look like these are the ones that I want. But you usually get a bunch of properties that you didn't expect would be there.
And another question I had, I'm assuming that you use this and then you elevate the ones you want into your test suite, and that's your test suite you keep using.
I definitely would recommend against running this and then generating the test suite and never looking at the test suite. That sounds like a terrible idea.
Do you have some examples of surprising properties that you found?
Oh, examples.
Like the one you just mentioned, but I don't know if you had any.
Yes, the sorted version of a list is always smaller than the unsorted version because of the ordering instance of lists. Is something I didn't expect to find, but showed up, and I'm like, oh yeah, that's true. I can also actually see if this works. let me actually. I can't actually look at my toy. My sort. Voila. Here is the sorting code that we saw earlier. And now I'm going to try to run.
Can you make it bigger?
Can I make it bigger? Probably not, but I can do this. Oh, come on. So here's the code again. And now I should be able to do easy spec on that. And voila, we get some properties of that code. So this shows you that it works for some specific examples. If I try to run this on any other code, for example, on itself, it just crashes.
Any other questions? Okay, thanks very much.
Thank you.